Let me give a brief introduction to today's speaker. Ting-Chun received his bachelor's degree from MIT, and now he is a PhD student at UCSD. He was an intern at HHQC when he was a graduate student at NTU. Therefore, I think most of us know him well. Today, he will bring us his recent work on quantum LDPC codes, and let's welcome him.
Yeah, hello. Hi. So can people hear me?
Yeah.
Okay. Yes. Okay. So today I would like to tell you about our recent results on a new family of good quantum LDPC codes. So these are code with constant rate and linear distance. And at the same time, they have like low connectivity. So this problem was first solved last year by Panteleev and Kalachev. But besides that, we also additionally showed that the new family of quantum LDPC code also have linear time decoder. Yeah, and this work is done with Eric Deneur, Mingshu Xie, and Thomas Wiedemann. Okay, before going to the detail, let me just tell you like why we care about error correction at all. Yeah, so as we know, like in real world, like if we want to build a quantum computer, then we know the quantum gates are more noisier than these classical gates. And this problem becomes very severe when you want to run a quantum circuit for a long time. So for example, in this picture, so you take your favorite circuits, and which has multiple gates. And say the gate error is like 1%, then when your circuit has like 100 gates, there will likely be one gate error somewhere. So let's suppose this bottom gate has an error with it. Then what happens is that after this erroneous gate, the 2 qubits afterwards becomes unreliable. Okay, and what's even worse is that since this qubit is not reliable, after passing through this gate, the 2 qubit afterwards become like also unreliable, and so on. So what happens is that when you run this circuit long enough, what you get is that all the qubits that you have at the end becomes unreliable at all. That means the result that you get after your computation is just noise. Yeah. So the way to solve this is by imposing these error correction at every layer, and yeah, and this will be very important eventually when we want to build a fault-tolerant computer. Okay, and yeah, so now we know that error correction is important. Then the next question is why we focus on these low-density parity check codes. And the reason is again because of the like the noisy property of these quantum gates. So okay, so okay, so let me first say a few words on how we do these error corrections in general. So the way you do error correction is by using the syndrome. And the syndrome is obtained by doing some kind of measurements. So for example, let's look at the picture below. So these black circles represents the like particular qubits. And these blue and red checks, these are some kind of measurements that is used to obtain the syndrome. So for example, when I draw this blue check and it's connected to these 3 qubits, what I mean is that this check, which will output 1 or 0, is obtained by performing some measurements on top of these 3 checks, on these 3 qubits. And importantly, this is a coherent measurement. So so you really have to, like, it's something quantum behind it. And what we know is that if this check is connected to many qubits, then these measurements would become more and more unreliable. And if the syndrome is unreliable, then we cannot do error correction. Since the error correction is based on the syndrome, if the syndrome is already unreliable, then we cannot do correction at all. So it will be desirable for these measurements to only involve a few qubits. And that's exactly what this low density is saying, low density and low density parity check. Yeah, and so more formally, this quantum LDPC code, it's actually not just a single code, it's a family of code. So we want the number of qubits to be larger and larger, so make it scalable. And at the same time, we want to keep this delta to be a fixed constant. Okay, so that's the, so now we know that we want to have these quantum LDPC code. And in fact, there are like two general kinds of LDPC code. And one of them is the surface code, and the other is the expander code. Yeah. So in fact, both of them are important. So I'll like make a quick comparison between them. So first of them is the surface code. So it's a family of code that can be embedded into a 2D plane. So for example, this Tor code, we'll talk more about later. But here we see that these black edges, these are the qubits. And then there will be some red check and these blue checks that would perform some measurements for the nearby bits. So the point is that all these measurements can be done locally in 2D. So just measure the things nearby. And that's pretty preferable for these superconducting quantum computers. On the other hand, these expander codes, so these would be the codes we'll talk about today. So instead, they don't have a simple embedding in 2D. What that means is that, okay, so you can think of this as, okay, there are a lot of, again, there are these red dots, and then there are these edges connecting them. However, these connections could be very far. So LDPC is saying that you only connect to a few other qubits. But here, for expander codes, these connections could be very far, and so these measurements could be harder to make. And so that's not a very desirable feature for these expander codes. However, on the other hand, so far it seems like surface codes is better, but in fact, they suffer another problem, which is that they have pretty low rates and low distance. So as we'll see, this Tor code can only store 2 qubits. So you see, you're using so many black qubits. However, you can only store 2 qubits. On the other, yeah, so that's like the disadvantage for these surface code. So on the other hand, for these expander codes, these recent results, it's saying that, in fact, these code could be very good, meaning that they have a constant rate and also like linear distance. And furthermore, our work shows that, moreover, you can have a linear time decoder. And this property could be very helpful when you want to like scale up your system. Yeah, of course, I should say that these are very far in the future, since these in order for these error correction to be actually actually being useful, you actually have to have many qubits, which we don't have yet. And maybe one more comment, which is that because these expander codes requires long-range operations, in fact, maybe the first quantum computer that uses error correction would likely be something similar to these surface codes. Yeah, but for this talk, we'll just focus on these expander codes. Okay. Yeah.
Sorry.
So now.
Hello.
Yes.
I have a question. So,
Okay.
the check is the measurement among some qubits, right?
Yes.
So here, the in this surface code, um, I don't, well, could you maybe explain a
Yeah.
little
Yeah.
bit?
Yeah.
Like because
Yes. Yes.
I
Right. I'll explain more later. Here, I'm just like giving a
okay,
really quick overview.
okay.
Yeah. So indeed, yeah. So now I'm going to go into more detail and tell you more precisely the definition of these LDPC and like these codes. Okay. So first of all, so we eventually want to talk about the quantum LDPC code, but first we'll look at these classical versions. So these are the classical LDPC code. Yeah, so what's a LDPC code? Well, they stand for these low density parity check code. Oh, by the way, can people see my cursor?
Yes.
Okay, good. All right, so yeah, so these LDPC code stands for the low density parity check. And it's a linear code that's over some bits and this parity checks. So these bits are depicted as these circles, and then these parity check are depicted as these squares, these blue squares. Okay, so each of these parity check is attached to at most delta bits. Okay, and that's what the low is about. So the low for the low density parity check. Okay, so what these parity check does is that it checks whether the XOR of the bits that it's adjacent to are equal to 0. Yeah, so in order for a like a label to be a code word, you have to pass through all the parity checks. So for example, the string is a code word because, so for example, look at this parity check. It's satisfied because it touches these 110, which add up to 0 mod 2. Yeah, and for this check, it's connected to 0 and 0, and which also add up to 0 mod 2. Okay, so that's the LDPC code, and we say the dimension of the code is the number of bits minus the number of checks. So in this case, it will be 1, which is 5 minus 4. And the distance, it will be the least weight of the non-zero code word. So here, weight means the Hamming weight. That is the number of non-zero entries. So here, the weight is 3. And the distance is looking for the lowest weight. Yeah, and ideally we want both of these numbers to be a constant fraction of n, and that's the so-called asymptotically good code. So these are code with linear distance and linear dimension. And it's also LDPC if these parity check involves at most a constant number of bits. And it's known that these asymptotically good LDPC exist, and they can also be constructed efficiently. So one of these works is called the expander codes by Zipser and Spielman. And many of the ideas for the quantum LDPC code also draw from that paper. Okay, so now we can move on to the quantum LDPC code. So in this case, here I will not tell you exactly how it's correspond to like a real quantum code, like how it's related to qubits, actual qubits. Instead, I'll just explain it as like two classical LDPC code with a certain property. Okay, so again, quantum LDPC code has some qubits, bits or qubits, and there are two sets. Now there are two sets of parity checks. So these blue checks are called the Z checks, and the red checks are the X checks. So the X and Z are referring to the X and Z Pauli operator. Yeah. But now we don't need to know them for this talk. So both of these codes should be LDPC, and in the sense that each of these checks has a constant degree. Okay, so in order for these two codes to be a well-defined quantum LDPC, they have to satisfy this orthogonality property, this orthogonality condition, and I'll explain more on the next slide. But assuming that, then you get a quantum LDPC code, and the dimension is again the number of bits minus the total number of checks, which is the number of z checks and the number of x check. Okay, so now let me explain what this orthogonality condition is. So for those that may know, these quantum codes are defined through the stabilizers, and the stabilizers has to commute, and that's exactly this orthogonality condition. So what it is that, so given any blue check and red check, so say this one and this one, you look at the number of shared qubits. So in this case, it will be these 2 qubits. And the condition is saying that it has to be even. So in this case, they share 2 qubits, so that's a good sign. On the other hand, we can compare this blue check with this red check, and we see that it also shared exactly 2 qubits. So that's also good. However, if we take the rightmost check, these two, then they only share 1 qubit, and that's bad. And that means actually, although I draw like this quantum LDPC, but this is actually not a valid or legitimate LDPC code. Okay. So one consequence of this orthogonality condition is that for every blue check, so I'll write a 1 over here. If you propagate out to its neighbor, so I write 1, 1, 1 for these 3 bits, and then 0 for other bits. This would be a code word for the red check. So what that means is that it satisfies all the red check. So for example, for this check, you have 2 1s coming in, and so they add up to 0. And so it's this check. So this is okay. So this is a code word, and we know that this code word actually has a low Hamming weight, at most delta. Because this blue check has degree delta, at most delta. And what this actually means is that this red LDPC would have plenty of code word with low Hamming weight, because each of these check would generate such a low weight code word. And this actually sounds like a big problem, because we know that we want to have code with linear distance. But here it seems like, okay, if we require to be LDPC, then it's a constant. And so the distance for this red check would also be a constant, which doesn't sound right. So the resolution is that, in fact, this distance of quantum LDPC will be defined in a special way, which I'll tell you now. Okay, so again, the distance would be the least weight of non-zero code word. However, non-zero here would mean that it's non-zero up to flipping the blue check. So when I say flipping the blue check, I mean the process of adding 1 to its neighbor. So adding 1 mod 2 to its neighbor. So if you can turn a red check, if you can turn a red code word all the way down to 0 by flipping these blue check, then we don't count for the purpose of distance. So for example, this 11100, this we don't have to consider it for the z distance, because we can turn it off by flipping this blue check. Okay, so for it to be a good LDPC, quantum LDPC, we want this distance to be large. So later we'll refer to this okay, yeah, since this distance has to be large. And in fact, here the red distance is large. In fact, we also want the blue distance to be large. And these two conditions are actually different. So we would call one of them the z distance and the other the x distance. And the total distance of the LDPC, the quantum LDPC, would be the minimum of the two. That means we want both of x distance and z distance to be linear to n. Okay, so any questions so far? Okay, so now we'll move on to an example. So that's the example of the Torah code. And that's so that's like the classic and pretty famous example due to Kitaev. And as I say, this will probably be the first, like the code that would be first applied to quantum computer with some level of like error correction stuff. Okay, so this Torah code has a parameter L. So in this picture, it'll be 4. And it gives like an L by L torus. So to get an L by L torus, you can start with this this grid, L by L grid. And what you do is you identify the left side with the right side. So what that means is like, okay, so this vertex would be identified to the vertex, this vertex on the left. Okay, and so as this right edge would also be identified with the left edge, and so on. So we'll wrap around horizontally. And also we would identify the top and bottom. So we'll wrap around vertically. So even though it's 5 by 5 in this picture, it's actually 4 by 4 after like identification. Okay, so now the bits. So I'll tell you where the bits and the checks are. So the bits would lie on the edges of the torus, and the red check would be on the vertex, and the blue check would be on the faces. And the incident structure would be the natural one, which is this blue check would check the 4 incident edges, so these 4 qubits, and then the red check would check the 4 neighboring qubits. Okay, and here delta would be 4 because each face touches 4 edges, and then each vertex touches 4 edges. And this actually holds for arbitrary large L. So eventually we will think of L as a growing parameter, so making this torus larger and larger. But no matter what, this delta would still be fixed. And that's exactly like this generates a family of quantum LDPC codes. Okay, so does that answer one of the questions about Torah code?
Yes.
Okay. Okay, so now I give you this structure, but now there's one very important thing to first check, which is this actually a legitimate quantum LDPC code? So that's the orthogonality condition. So how do we check it? Well, recall we take a blue check and a red check, and then we count the number of shared incident bits. So if the red check and the blue check are too far apart, then they don't share any bits, and so it's 0, which is even. And when they're close, then it would look like the picture below. And here you can see that it shares exactly 2 edges, and which is even, and that's good. So this is a good, this is a legitimate quantum LDPC code. And now we can begin to ask its distance and its dimension. So let's start with dimension because it's simpler. So as I say, the dimension of these codes are pretty low, which is 2, which is not so good. However, it's not 0, so at least it's not trivial. So let's see, how do we see it's 2? Okay, so the dimension is the number of bits minus the number of checks. So here there are 2 L square number of bits. So you can see that. So one way to see that is the horizontal edges. There are L square number of them. So is the vertical edges. So L squared plus L squared gives you 2L squared. And what about the red check? So naively, it seems like there are L square number of red checks. But actually, if you add up these checks, they cancel out. They cancel out to 0. So what that means is that one of them is redundant. And so in reality, there are only L square minus 1 independent red checks. And this is the same for the blue check. So overall, you get the dimension 2. And this is, so this is 2 no matter what's the size of L. And that's the problem, because we want this dimension to be linear to L. Okay, so that's the dimension.
Can you explain again why there's a redundant there?
Again?
Why there is a redundant L square minus 1? Redundant.
Okay.
Yeah.
Yeah. So why is it redundant? So here's the reason. So so say this red check, it's checking the sum of the 4 neighboring bits. Okay, so it's saying that, okay, the sum of these 4 bits should be 0. Okay, and so that's for this check. But for this other check, it's also doing the same thing. What happens is that, okay, so say you add up this relation for all the checks. Let me do it this way. So say you add up these 2 checks. What happens is that it's saying that the sum of these 4 bits is 0. Okay, let me put it in the other way. So let's scroll up here. So let me use blue as an example. So this blue check is checking these 3 bits. And when I say that the checks add up to 0, what I mean is that this relation, the check is imposing a relation on these 3 bits. This relation can be written as a vector. So this 1, 1, 1, 0, 0. And in fact, if you write out the L square number of vectors, you found that they're linearly dependent. So that means that so you can remove one check, which still define the same code. So it's a redundant check, and that's why we have to remove, like we cannot count it for this computation.
So the basic question, for each check, they want to just check, are they summing up to 0, or they are just checking 0, 1, right? Summing up to even number or odd number, just this kind of check.
Oops. Can you repeat that again? Are you saying that is the check just checking the sum of the bits to be even, or to be 0?
Yeah, to be 0 or even. Yeah.
Yes.
Okay.
So doing that, and equivalent, you can think of it as multiplying the bits string, the bit string to this one, to this, like, okay, so this check says that, okay, the sum of these 3 bits should be 0, and you can equivalently think of this as when we multiply a code word, when we multiply the code word to the vector 1, 1, 1, 0, 0, it has to be 0. So inner product of 2 vectors.
Sorry, 1, 1, 1, 0, 0. Why there is adding up to 0? There are 3, 1. So you mean a combination of them? How to arrange the check to give them sum up to 0?
Let me see if I can draw. Okay, I cannot draw now, but I can explain more later.
Okay.
Maybe when I connected using iPad.
Okay.
Okay, so right, so we're at distance, and then I kind of say that's one of the check is redundant, and that gives you dimension 2. So now we can now we'll look at the distance of the toric code. So so recall so the distance is defined in this special way. Okay, all right, okay. So eventually we want the red distance and the blue distance to be, both of them to be large. And in this case, because there is a duality between red and blue, so actually we only need to study the red distance. So at first you may think of this, so here, okay, so let me give an example of a code word, red code word, so which is this 1111 string. So this is 111 on 4 of the edges and then 0 everywhere else. And if we can, for each of these red check, the sum of well, it's incident to even number of ones, so they add up to 0. So this is a red code word. Okay. And actually it has a pretty low weight, it is 4. So you may think that, oh, is the red distance 4? But remember that they don't actually count, because we can turn it into 0 after flipping the blue check. So that is, if we flip this blue check, then we would add 1 to all its neighboring edges, and we turn this code word into 0. So it's actually a 0 code word, and so it doesn't count. And this is actually the same for this other code word. So again, this code word looks like a loop, and you can check that each of these red check is incident to even number of ones. But again, this doesn't count because we can flip these 3 blue checks. So the top edge would add another 1, which turns into a 0. This gray edge would add 1 twice and still a 0. And actually, the whole thing would just be turned into 0. So again, these two doesn't count.
David, can I confirm one thing first?
Yes.
So when you say bit check means that you're pairwise check with neighbors, and red check means So bit check means there's a difference between a black, red, blue. Does mean that how many pair you are checked simultaneously, or I don't get that. When you say face, does that mean you check the 4 pointer at the same time? No.
Yes. So
Yes.
So the blue check, what it does is it requires this. Okay. So the blue check requires the sum of the 4 neighboring edges to be 1.
Yeah.
To be 0. Okay, but okay. I think there is one confusion, which is that when I draw 111, 111 here, you may feel that, okay, this seems to violate the blue check because it adds up to something that's odd. Yeah, so that may be one confusion. So the resolution is that actually there are two kind of code word to look at. So currently we are studying the red distance, so we're looking at the red code word. Okay, and what the red code word is, so if we look at this picture, it will be the qubits such that if you perform these red checks, so these red checks requires the sum to be 0 in this example. So so red code word would use the red check, and the blue code word would use the blue check. So these are two separate things. And here we're focusing on the red check, or the red code word.
Okay.
Does that answer the question?
Yeah.
Okay. Okay, so again, we're looking at the red check. So when I say this is a code word, red code word, what you want to check is you want to check all these red things is incident to exactly even number of ones. Whereas for this blue check, you don't have to worry about them. what you want to care about them is you want to flip them. That's the usage of these blue checks. Okay, so these two, as I say, they're red code words, but we don't count them because they can be flipped to 0. So what would be a non-trivial code word? So as we see, these has some kind of loop feature, and in fact, this non-trivial code word would corresponding to a non-trivial loop. So as I say, this is a torus, and for a torus, there are two, well, at least two. Well, there are two non-trivial loops. So one of them is this horizontal loop, and one of them is this vertical loop. So again, remember that the top vertex is identified with the bottom vertex. Yeah, and you can see that when I put 1 on these edges, it passes all the red checks. So indeed, it's a red code word. However, you can also see that adding blue checks doesn't help much. Because if I add a blue check, it's still a loop. And this loop still goes around the torus. And okay, so now, as I claim, these two are non-trivial loops, or non-trivial red code words, and they have weight L. So the red distance is L. And you can do the same for blue check, which is what you found is that it's also the blue distance is also L. Okay, and this actually, yeah. So is there some question here? Okay, so this actually brings up to the history of the studies of LDPC codes. So the code that we just described is this Torah code. So the first one, this Torah code by Kitaev, and we show that the distance is square root of n. So recall that the distance is L, but there are L square number or 2L square number of qubits. So the distance is only square root of n. And again, the dimension is 2, which is both not so good because we want both of them to be large and hopefully proportional to n. But that's what we have at the time. And shortly after, there is a well, one can think of Torah code as a tensor product of repetition code, and if we replace this repetition code with a better LDPC code, in fact, we can bring the distance to n. So the remaining question becomes, how can we improve the distance? So how can we improve the distance beyond square root? So there are some development between these two works, but the improvement is only marginal. So we can improve it by some polylog factor, but not a polynomial factor. So the first breakthrough is indeed this fiber bundle code, which appeared 2 years ago, and they bring the distance to beyond square root n by a polynomial factor, which is pretty important. And soon after, once people begin to realize, okay, this is actually a possibility, this PK, the same PK I mentioned, they actually bring the distance all the way to n divided by log n, although the dimension is pretty low, only log n. Anyway, the point is that by combining these related ideas, you can bring both the distance and the dimension all the way to n, linear to n. So that's the breakthrough I mentioned. And for us, for our new result, we provide a new construction which both of them are linear. However, the dimension is only actually 1/2, at most 1/2 times n. But it's still linear, so that's also good. What's even better is that these constructions have a simpler proof, and by doing a bit more, you can extend this to the linear time decoder. So we also show that the code we constructed has linear time decoder. And on the other hand, almost around the same time, 2 other group of people also solved this linear time decoder question. And the code that they're working with was the previous these two codes. So basically, what we understand now is that all the codes that we know of has good distance and at the same time can be decoded efficiently.
Hello.
Yes.
So previously you mentioned that the torical only represent 2 qubits, right?
Yes.
So could you explain a little bit about that? Like, how do I see is 2 qubit?
So that's related thing I'm saying here, which is
Okay.
that yeah.
Okay. Then maybe another question is that I kind of confused. So the parity check for the blue one and the red one. So one is like the blue one is I restrict them to be summing up to 1 and the red one summing up to 0. So my qubits have to be a state to satisfy these two checks. Is that correct?
So actually, let me say again. So there are actually two kind of code word. So we will call it like the red code word and the blue code word.
Yes.
Okay. So actually, for the red code word, it only has to satisfy the red check. So it doesn't have to worry about the blue check at all. It only has to satisfy the red check. So that's for the red code word. Okay. On the other hand, you have this blue code word, which is separate. This blue code word has to satisfy the blue check, and it has nothing to do with the red check. Okay. So it's indeed like two different codes, two classical LDPC codes.
Okay. So say I have 5 qubits and in some specific state. And so each time I only either check the blue checks or the red checks. So when I check the blue check, it is in maybe 11100 and it satisfies blue check. And then when I check the red checks, and maybe I have like 10100 and it satisfies the red checks. Is that correct? Is it like that?
10110.
Oh, I just randomly pick some string.
Okay,
I just say they are different. So yeah.
Right. And actually, I realize there is a confusion. So let me clarify. Let me clarify even more. So currently, my description only I've like changed the description, so it's only talking about classical codes. And in this setting, it's exactly what you say, and which is that these two codes are separate. So to study quantum LDPC, we can think of as studying two classical codes.
Okay.
However, this is the description that we use for this talk. But on the other hand, for a more physics perspective, you have these bits are actually qubits. So because it's a qubit, you cannot simply write it as a bit string. You cannot just write it as 11100. It's a superposition. So in that description, indeed, you actually check both sides. But that's a different description, which I'm not talking now.
Okay. Okay, sorry. Another naive question.
No problem.
So, like, why do we check these code words?
Yeah. So you're asking why?
Yes. I'm not familiar with this. Error correction things. Sorry.
Oh, okay. Actually, let me see. Maybe the same question also applies to the classical. So maybe you would also wonder like why we describe a linear code using parity checks.
Yes.
Okay, good. Okay, so this one I can answer more easily. So for example, let's say you have a code word. So the idea of error correction is that I would encode my information into code words. So maybe, so that's what this dimension k is about. So what this dimension k is of a code means that this code allows me to encode k number of bits into n number of bits. So I'll use n bits to represent k bits. So there's a redundancy there. So usually n is greater than k.
Okay.
And this redundancy allows you to perform like correction. And the idea is the following. So say you have a code word, then the parity check would always be 0. So the sum would be 0. However, if like say this bit is flipped, so this third bit is flipped, then what you found is that these two parity check would be violated. Okay, the first two parity check would be violated. So oftentimes you can use this information to infer which bit is incorrect. Okay. And so this is actually, so these one, so for example, the example I gave, this one at the center of the bits would be the error, and then the one that you computed by summing up the bits at the check, these would be called the syndrome. So that means the syndrome 1100 would correspond to the error 00100. And that's the kind of the rationale of these error correcting methods. So we always measure the syndrome, and then we use that to infer the error. And once we know the error, we can like correct it. That's the idea.
And then, what is the distance d here again?
And with the distance d here, it usually means like how much error you can resist, or how much error you're resilient to. So what this distance say is that, okay, if I have d let's say d divided by 2. Say you have d divided by too many of errors, then the code with distance d would still be able to correct it.
Oh, okay. Like so, like if I have like two arrows, so like maybe certain checks could not verify it because it shows up in pairs, maybe like that. So distance d is to say I allow how many bits in my bits to be arrow, something like that.
Right.
Okay,
So
thank you.
yes, exactly.
Yeah.
So,
can I ask a question?
Right. Okay.
Yeah. I want to ask why the first blue check connect to 3 bits and the second check connect to 2 bits. Is there any design idea behind it?
Okay. Eventually this graph has to be designed carefully. But for now, I'm just drawing an example.
Okay, so you mean there's many possibility to do this LDPC code, right?
Yes, exactly.
Okay, thank
you. Sorry, I ask a quick question. Once the code words change, like 110001, change to other setting, and does the connection has to be changed for this parity check to remain them adding up to 0?
Can you repeat that again?
I mean, for different code words.
Okay, for different code words.
For the n qubit, these are code words, right? And then, does the connection has to be changed of the blue check, the connection, like the first connect to the first 3, the second check connect to the 2 bits. Does the connection has to be changed corresponding to different code words, or you are designing a connection?
I see. So the idea is that given a connection, then you define a code. So code, then from the, so with the code is like a set of code words. So so if I directly answer your question, it will be that let's see. So if you change the code, then you will also change the connection. And if you change the connection, you also change the code. But code word is a separate idea. So code word, so So once you define the connection, you can ask, oh, is this code word part of the code? So that is, does this code word satisfy the property where the sum of these parity check, or of these bits that's adjacent to the parity check, sum up to 0?
So you want to make this subset as large as possible for this connection. That's the idea.
Yes, and the size of the set is determined by, so the size of the like the code word, number of code word is related to the dimension k. So
Okay.
2 to the k, 2 to the k.
Okay. Okay, I see. Thank you.
Okay. Okay, I'm a bit running out of time, but let me kind of go through the rest of the stuff. Okay, so let me state our main results. So just to make it more formal. So what we can show is that for any rate less than 1/2, oh, sorry, rate. I haven't defined the rate. So rate is the ratio between dimension and n. So that's dimension divided by n. So let me just do it very quick. So, okay. So rate is k divided by n. And then later we'll use the relative distance, which is also d divided by n. So we're always looking at the ratio between the two. K and n, and then d and n. So that corresponds to RA and delta here. So what we say here is that for any rate less than 1/2, and then for, okay, there exists certain codes with rate less than 1/2, and then also a certain distance, which further has the property that you can decode up to that distance, delta prime, in linear time. So as I kind of allude before, if you don't care about having an efficient decoder, then you can usually decode up to delta divided by 2. If you don't care about time complexity. And here we're saying that you can actually do this kind of operation very short in linear time. So, and let me, so in the later part, I was hoping to tell you about the construction, and let me see like how much I will be able to say. So this construction is motivated by one of the paper by like one of the author, Eric Deneur, and with other co-authors. So they use, so that their motivation was to solve another problem in coding theory called the locally testable code. And turns out locally testable code has a lot of relation to these quantum LDPC code. So here we're able to use their construction to show our results. So this construction uses the Tanner code by combining the left-right Cayley complex and the robust code. So we'll quickly go through them. Let's see. Okay, maybe I'll tell you what's a Tanner code and then I'll leave out the rest. So a Tanner code, it's an LDPC code, but it's more sophisticated. Again, this Tanner code uses has a graph. Okay, so here is the graph, again, the bipartite graph. And you have the bits and then the checks. So the blue bits are the black circles and then checks are the squares. And here we'll assume it is regular, meaning that each of these blue check is connected to exactly delta number of bits. So here it's 4, 4, and 4. So it's always 4. So in this previous picture, we say that, in the previous picture of LDPC code, we say that like a green label, it is a code word if we add up the bits connecting to the check, it's 0. That's the previous picture. But now for Tanner code, you actually do something else. So what we do is that we additionally have this small code C. So it takes in delta bits. So it has the parity check matrix H. Okay, so what it requires is that, so we say a green label is a code word in the Tanner code if for every blue check, so we look at the delta bits connecting to it, instead of adding up to 0, you require them to be part of the code word in C. Yeah, equivalently, it's saying it means that it has to satisfy the parity check in H. So even though this Tanner code looks like a different construction, well, because you're checking the bits falls into certain code instead of just adding up to 0, but it's actually still a standard LDPC code. So that's I will now explain. Okay, so the idea is that we can turn this Tanner code into an LDPC code described before by doing the following operation. So what we do is we split this big check, this old check, into like smaller checks. For example, this H has these parity check has 2 rows. Then this big check will be split into 2 smaller checks. So let's look at this second check over here, which corresponds to the second row of H. So the second row of H is 0, 0, 1, 1. Then so this check would be connected to the later 2 bits. So the third bits and the fourth bits. So that's to say the check is incident to the bit whenever there's a 1 in the entry of H. And we can do that for each row. So this 1, 1, 1, 0 would correspond to this 1. So it's connected to 1, the first one, the second, the third, but not the last. Okay. And as you can see, this operation is the same as requiring the 4 bits to be inside the code. Now you can do this operation for each of the check. So then you get the all kind of classical LDPC code where each of the small check is doing an XOR operation. Yeah, so that's a Tanner code, which is still an LDPC code, and we'll use the Tanner code to construct our code. And let me just tell you a quick variation. So instead of putting the bits, so here we put the bits on the vertex. In fact, we can also put it on the edges. So here we again have a bipartite graph, which again is regular, meaning like each vertex is connected to 4 edges. Yeah. Okay. So, but however, now we put the bits on the edges. Again, yeah. So again, when would this label be a code word? It would be that for each check, we require the 4 bits to be a code word in the small code C. Okay. Okay, so that's a classical Tanner code, and that's the most important building block for us. For our construction, we will be using the 2D Tanner code, which I'm just currently giving you an idea. So the idea for our construction is we generalize this construction to 2D. So we will construct a 2D Tanner code, which combines a 2D graph with a 2D small code. And here I'll just show you the picture. So this is the 2D graph, which contains these vertices, edges, and squares, which is kind of similar to these Tor codes, but it's more general. So that's the graph. Then you can combine with this code, small code. So what it does, it takes it consists of two codes, H1, H2, and you can kind of do a tensor product and form this kind of interesting, like you see a lot of squares in all these pictures. So here it's like, it's saying that if you start from this vector space, if you go up and then right, it will be the same as going right and up. So it's some kind of commuting property. And what's nice is that in 1D, we kind of combine these two things to form the 1D ternary code. You can do the same operation here. What I'll roughly tell you is that we can split this red check into like a matrix. We can split one vertex into multiple vertex as if it's a matrix. And on the other hand, we'll split these bits. So previously we only split the checks, but now we also split the bits. So you split the bits into multiple bits. And that's for the purple bits, but also we also do that for the this brown bits. And what you found is that this geometric picture on the graph, so over here it becomes like a code, the picture of the code on the bottom. And that's kind of the idea of how you combine everything together. Okay, so that there are some conditions. So here I'm just telling you, okay, you can combine a graph with a code to get a ternary code, but actually these graph and also the code has to satisfy some particular relation. What I'll say now is that yes, these can all be done. Okay, so the summary. So we'll just go to the summary. So here we construct a good quantum LDPC code using this ternary construction by combining left-right Cayley graph and then the robust code. Here we'll do a quick comparison with some other related papers that I mentioned. So in fact, our construction is pretty similar to this PK, this earlier construction. So on the left, it's our code, and on the right, it is their code. And what you see, the difference is just that they replace some red check with some bits, and then they replace the bits with the check, and that's it. So it's very, very related. However, our proof is much simpler because we use so I mentioned there is a code property, this robustness that has to be satisfied for the small code. And in fact, in this paper, we also proved that you can achieve very good robustness property. And that actually simplifies the proof a lot. And moreover, this proof technique can be generalized to this proof for decoder, and that's how we got our results. So I mentioned that besides this PK construction, there's also this LZ construction, and that construction is quite different. So it's kind of its own, it's like a special construction. But on the other hand, this construction, it could have some advantage in practical settings because its construction is more even. So I'm not saying more, but if you're looking for more practical applications, maybe that's a good example to look at. Okay, and finally, I'll just tell you some other short discussions. So this work, although I phrase it in terms of these quantum pictures or these codes, actually, more abstractly, this is related to the property of chain complexes. So some kind of expansion properties. And so I'm just throwing a keyword. So that's the high dimensional expanders. So that's actually one of the, so our proof is kind of phrased in terms of this kind of language. What's very nice is that from this perspective, high dimensional expander, we can understand, we can generalize this construction even more into higher dimension. So at first I mentioned there's the 1D ternary code. Now we construct the 2D ternary code, but actually the same construction can work even more into 3D to 4D and arbitrary large dimension. And it will be interesting to see if they have some interesting usage. And one of them could be this quantum LTC. So this is another open question that has been that people have been thinking about for a long time, and this recent progress could probably shed some light to that problem. Among them, there's a very important conjecture, this NLTS conjecture, which is actually solved recently using this series of results of quantum LDPC codes. Okay, and that's everything. And here's the oh, that's not the paper. So the paper. So that's the paper. Okay. So yeah. So any questions?
Okay. I think I still not get like how do you encode it to a qubit, because I feel it's more like you have a code word and you can correct it, but so like I design my check to make it like a like 000, only a set like 000, then if one is flipped, I just correct it back. So my qubit is like this, like my logic qubit is 0 if we satisfy the check.
Okay. So you want to talk about quantum settings. Okay, have you heard about the stabilizer formalism?
No.
Okay, good. So that would be the first thing to look for. So currently I phrase everything in the classical picture, but actually there's the so-called like stabilizer formalism. What stabilizer is, it's also like a check, but it's a quantum check. So it's not exactly as what I described here, like 110. It uses these Pauli operators. Yeah, and
okay.
then that's yes. So actually Pauli operators would enter in those settings. Yeah, and actually there is an important question I didn't address at all, which is the problem of like how do you encode, like, okay, currently I'm just doing the classical setting, but in the quantum, like if you move back to the quantum, you can ask how can I encode a quantum bits into this quantum code, and that's not so simple, but we're not describing here. And to answer that question, you really have to go back to the quantum setting.
Then like your work is to apply on maybe some classical cipher system.
Okay,
Like
so
what?
So actually this result still indeed construct a quantum code.
Mm-hmm.
It's just that I'm just using a classical, because a quantum code is equivalent to these two classical codes. So that's why I'm using this description, and they're actually equivalent.
Okay.
Yeah, but the equivalence, to understand the equivalence, you have to go back and understand the stabilizer formalism, etc.
Okay. So like so you just change your check to the stabilizers, then like your code is then can be the error correction code. Is that correct?
Yeah. Yes.
Okay.
So this distance or this dimension exactly corresponds to the quantum. So this dimension k would correspond to how many quantum bits you can code into this code, and also this distance, this quantum distance, would also correspond to how many error you can sustain or resist.
Okay, thank you.
So these definitions are all motivated by the quantum setting.
Hi, David. Thank you for your talk. I want to ask two questions.
Yes.
And the first is for the comparison. You mentioned your setting is similar to the previous work, but it looks to me the previous work are changing the law of check and bits, but you are expanding them to higher dimension. Are the two equivalent, or do I misunderstand something? Here, the do you change the law of check and bit here? And,
yes.
but
yes.
you are not doing this. You are expanding them, right?
Yeah, I'm explaining it. So I'm saying that the PK construction is similar to ours. So this is the on the right is the PK construction, and in what way they're similar? They're similar by like changing check into bits and bit into check.
So you're doing the same thing?
No. Here I'm so on left, this is exactly what I did. So this this red is the check, and this purple and then the brown is the bits.
Okay, and my second question is, you are expanding them for check and bits, you are expanding them to larger dimension, higher dimension, like a tensor product to different separate things. And then, so you are talking about the tensor product of them, and you are imposing some robust property on them. So it means that the tensor product is not a simple tensor product. You need to have some constraint on them. Is that correct?
Right. So the higher dimensional version would be, again, that you do a Tanner code, but you have to use some 3D graph. So here it would be a 3D graph and a 3D code. And again, like this 3D code also has to satisfy some robustness, which I didn't tell you, but there's also a 3D version of those conditions.
So it's not a simple extension, because when you go to higher dimension, the robust condition will make the condition quite different. Is that true?
Okay, so yeah, so apparently it may seem different, but if you use this high dimensional expander using their language, then they're very related. However, as you say, this generalization is easy in the sense that you can combine them. However, it's not easy in the sense that we don't yet know if there's a robust 3D code. So here we show their existence of robust 2D code, but we actually don't know if robust 3D code exists, and that's indeed a problem.
And this can be written in the language of chain complex, as you said. So this is how they are combined. Or
okay, so using the language chain complex, I think the uses is more like, because chain complex gives you a more natural language, so you're more likely to be in the right direction, kind of like that.
I'm asking in language describing what? Describing how they are combined, or how the dimension change, in which way the language is useful.
It makes the definition very simple. That's one way to say it. So
okay.
So early time there. Okay, so actually robust code also have a long history. So it's actually motivated from these locally testable code problems. But over there, the definition is not like, okay, the definition is natural, but it's not obvious how you generalize to higher dimension. Like you don't know which generalization is preferable, etc., etc. Yeah, at the same time, this is kind of like 后见之明, etc. But I can tell you that using chain complex, the definition will be much simpler.
For describing robust code.
For defining robust code, yeah.
I see. Okay. Okay, thank you. Yeah, thank you for your very nice talk.
Thank you.
Is there any further questions from the audience? Okay, if there is no further question, let's thanks David again. Yeah, thank you.
Thank you.
好，点君谢谢。好，哎，我们等一下。